I'd like to welcome Jacqueline Sporie from UW-La Crosse, whose presentation is entitled Why Zinc Oxide? Take it away, Jacqueline.
Okay, so hi, my name is Jacqueline Sporie. I'm a senior at UWL who has been doing research in material science and physics for about the last 3 years. And pretty much during that whole time, my project has been focused on the formulation of graphene zinc oxide thin films, which is actually the focus of my presentation, not just zinc oxide. But composite materials of zinc oxide and graphene are currently of great interest in the material science community because they are inexpensive, they're non-toxic, and they boast an incredible spectrum of useful applications. So we started out with zinc oxide, and we chose it because as a semiconducting oxide, it has potential as a photocatalyst due to the properties it possesses. And some of these I've included on the slide, such as large excitation energy, deep violet, borderline ultraviolet absorption at room temperature, and good photocatalytic activity. However, unfortunately, with zinc oxide alone, it is not our perfect photocatalyst. The main issue zinc oxide faces as a photocatalyst is that it has a rapid rate for the recombination of electron hole pairs. And since the photoactivity of a catalyst is determined by its ability to create photogenerated electron hole pairs, having a fast recombination rate can interfere with this reaction process. Next. So in order to mitigate this while maintaining the numerous desirable properties that I mentioned of zinc oxide, we brought in graphene. And the conjugated structure of graphene enables the separation of charge in the photocatalytic process. So by combining zinc oxide and graphene, the recombination rate could be slowed while hopefully retaining the beneficial properties of both materials. So essentially, we're taking a good photocatalyst, zinc oxide, and making it a great photocatalyst by adding in graphene. And together, zinc oxide and graphene have the potential to form a transparent conductive material that would have numerous important technological applications. Next. So I could include so many different applications for this material on this slide, but it could get a little bit obnoxious. So I've included some of the most interesting to me that we've been looking at, and that includes things such as semi-automatic heart valves that could function with the natural electrical impulses of the heart, many different biological applications since it is a non-toxic material, flat panel displays, photovoltaic cells, and numerous types of sensors, such as gas sensors, and much more. So as you can see, this would be a super versatile and beneficial material. And now that we have our desired properties and elements with zinc oxide and graphene, we had to find a way to combine them into a cohesive structure and create sheets that would eventually become the materials to work for the technological applications that I mentioned. Next. So that led us to graphene zinc oxide thin films. So we needed to find a solid method of combining the graphene and zinc oxide while maintaining their desirable properties and creating an enhanced photocatalyst, as I mentioned. And this has proven to be a great challenge, and creating a method to accomplish this has been what our lab has spent the majority of our time on. For about the last 1.5 years, we've been set on creating graphene zinc oxide thin films in this way. And we can do it in about 5 minutes for each using only ethyl acetate, millipore water, a petri dish, and a zinc oxide and graphene powder suspended in the organic solvent NMP. And it has proven to be extremely cost effective, efficient. It requires almost no intervention. And we have been seeing results with uniform films being produced, which is one of our greatest goals. Next slide. So here I have some examples of what the filmmaking process looks like. So essentially we start out with a petri dish filled with a small amount of millipore water, and then almost simultaneously add ethyl acetate along with our graphene zinc oxide suspension. And as the process begins, you will begin to see the petri dish, bubble a little bit in a sense, and then begin to see bits of the graphene begin to flocculate together. And we pretty much contribute this occurrence to Rayleigh-Bénard convection, going on in the liquid phases involved. And as you see the graphene platelets begin to flocculate, you will see them come together, pull apart, readjust, come together again, which is illustrated more in detail on the right picture on the right side of the screen. So essentially the graphene in a way is creating the uniformity for us and doing part of the work, because it will come together, come apart, readjust, find a better location. And then we end up with what we see in the left picture at the bottom right, which is a circular uniform thin film, which we then scoop up out of the dish currently with glass. And we've been analyzing them using scanning electron microscopy and a few other characterization techniques. Next. So we have found a lot of success in this process now, and it is really looking promising for us. We're very excited about it. And currently we've been doing this process using a solution of 10% zinc oxide combined with pure graphene platelets. And going forward, we're hoping to shift the concentrations around a bit outside of just 10%. So go in kind of increments of 10, of 1%, all the way up to 40%. Analyze said films and see which ones contain the properties that we like at the best level, such as photocatalytic activity, the semiconducting, and all of those properties, and then kind of focus in and hone in our formula for making the films. Additionally, since we have gotten a bit of confidence with this process, we're hoping that in the future, instead of limiting our films to zinc 2 oxide, that we could use other similar oxides, since they would have clearly very similar properties to zinc 2 oxide. This may include, for example, copper oxide, which could potentially yield results such as antibacterial, antiviral properties. And this same process could create numerous different kinds of materials out of oxides that would have very different and very beneficial applications. And that is what I have for you today. Thank you for allowing me to present.
Great, thank you, Jacqueline. At this time, we'll open it up to questions. Does anyone have a question? And if so, please just turn on your camera and unmute yourself and go ahead.
I have a question. Jacqueline, could you talk a little bit more about what properties you characterize after you make the films, and what are you looking for when you're varying the concentration? How you're looking for those properties to be optimized?
Okay, so right now we've really been focusing on, after collecting the films, we really want to just make sure that we are getting uniform film, because if we're seeing, bits of graphene here, high concentrations of zinc oxide on the other side of the film, that would totally mitigate what we're going for. So the first way we're characterizing our films is, as I mentioned, with SEM, scanning electron microscopy, looking for the different elements on the films, making sure that they're dispersed equally and whatnot throughout, because that is one of our biggest goals, is first making sure it is uniform. So with every film that we make, we complete scanning electron microscopy on it first.
So if I can just summarize, like you're looking for certain areas of uniformity, like the size. There's this many square micrometers of uniform graphene and zinc oxide. Is that fair?
Well, we're looking for a uniform combination of graphene and zinc oxide together. We want to make sure they aren't somehow separating in the filmmaking process, because ultimately we want it to be a very cohesive structure. So we're looking really for an even distribution of the two, kind of a marriage throughout the film, but yes.
Thank you.
Gokul, yeah.
Yeah, I was just wondering, Jacqueline, if you could tell me just what thicknesses these films have and what kind of thickness variation you're observing, and how do you measure these things?
So with the thickness, we're essentially looking for a uniform single sheet of graphene. And then we're hoping it's like 1 millimeter thick about, I think, or nanometer, but we're hoping to get, as thin as possible, basically, with the graphene. And then hopefully with those sheets, as we have sheets that are as thin as possible, then add sheets on top of each other to create the larger material structure. So the films are extremely thin. we do use scanning electron microscopy for that as well as a few other measurements. I can't remember all of the different ones off the top of my head, but the films are extremely thin, and that is what we are going for right now.
Okay, thank you.
So Jacqueline, I was wondering if you know how does the zinc oxide interacts with the graffiti, or if it's a multi-layer film or just a thick film.
So I think I know what you're getting at, but so this whole time in the lab, we have been trying to essentially put zinc oxide and graphene together in a way that they don't naturally want to, because what we don't want out of the thin films is a layer of graphene and then a layer of zinc oxide. We want them combined cohesively. So are you asking like what's happening in the dish as they're combining, or?
Yeah, how do they combine, or if they don't combine, or they just get together forming a single layer or not, or is it a multi-layer film?
Okay, so it's not multi-layer, it is a single layer. And essentially there's two liquid phases involved within the film. And what's happening is the graphene, once it's added, is migrating towards the surface of the film. And then there's lateral assembly occurring. And basically the ethyl acetate is what is allowing this process to occur through Marginoli forces, Rayleigh-Bernard convection. But it's a two liquid phases happening that put the zinc oxide and graphene together.
Okay, thank you.